SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss about turbulent flow and heat transfer in a pipe. Now, before we start our discussions over pipe, we can discuss a little more general topic. Actually, when we solve turbulent flow in a given geometry, there are many approaches. One of the approaches is basically solving through K epsilon model of turbulence. I am discussing this because we have already discussed the first part of it, that is basically governing equations for turbulent flow on any geometry can be written as continuity equation on the time average component of velocities. Time average components of velocities. So this can be depicted as del x of u bar plus del y of v bar plus del z of w bar equal to 0. So this is a continuity equation. As I said, divergence of ui bar. Ui in Cartesian coordinate, ui bar means u bar, v bar and w bar. So similarly, we can write Navier-Stokes equations, three equations written in tensor notation. As you can see, del t of ui bar, uj bar into del xj ui bar equal to minus 1 by rho del xi p bar plus del xj within bracket nu del xj of ui bar minus ui prime uj prime over bar, and this is the basically contribution of Reynolds stress tensor. Then the energy equation del time of T bar, T is temperature, uppercase T, ui bar del xi of T bar equal to del xi of alpha del xi T bar minus ui prime T prime over bar. This is also contribution of turbulent mixing. And this Reynolds stress can be expressed as minus ui prime uj prime over bar equal to nu t. This is eddy viscosity or turbulent viscosity del xj of ui bar plus del xi of uj bar minus 2/3 k delta ij. Delta ij is Kronecker delta and k is the turbulent kinetic energy. Also, we can write to close this mixing driven component of heat transfer, that is minus ui prime t prime over bar equal to alpha t del x I of t bar. And in this system of equations, this basically we can see nu t and alpha t are not known. Now, one a priori information is if we know nu t, alpha t can be determined. Alpha t is related to nu t by sigma t is alpha t, and sigma t is nothing but turbulent Prandtl number. This for a given fluid, usually this is known. So if we calculate nu t then and divide it by sigma t, we will get alpha t, which is turbulent diffusivity or eddy diffusivity. So eddy viscosity and eddy diffusivity, if these are known, then this system of equations can be closed, and over a given domain we can get solution of Navier-Stokes equations, which will give us the velocity field, and then solution of energy equation, which will give us the temperature field. Now, as we have already mentioned, sigma t is turbulent Prandtl number. The entire system of equations can be closed is sigma t is known and nu t is determined correctly. We can construct an expression for turbulent viscosity or eddy viscosity in terms of two attributes of an eddy. The eddy viscosity can be viewed as a product of velocity scale and a length scale. In case of turbulent flows, the velocity scale can be expressed as k power half, turbulent kinetic energy to the power half. And the length scale can be shown to be k power 3 by 2 divided by epsilon. Epsilon is dissipation rate of turbulent kinetic energy. So from these two we can get nu t. We have already said nu t is function of these two, and then they can be finally written as c mu k square by epsilon. And if this is known, then nu t is known. If nu t is known, alpha t can also be determined. Now, this quantity c mu is a model constant to be determined accurately for a specific flow. The kinetic energy k and its dissipation rate epsilon are evaluated at each point in the domain from their governing differential equations. The equation for k can be derived from the Navier-Stokes equations by subtracting the mean equations from the unaveraged equations to obtain an equation for the fluctuating velocity, say ui prime. Taking the scalar product of this equation with fluctuating velocity uj prime and averaging yields the equation for Reynolds stress transport. That means transport of u I prime into u j prime bar. The transport equation for kinetic energy can be obtained by substituting j equal to I in the Reynolds stress transport equation. An equation for dissipation can be derived from the Navier-Stokes equations by an extension of the method deployed to derive kinetic energy equation. So we get kinetic energy equation and the equation for dissipation rate of turbulent kinetic energy. And after analyzing, also it is found that these equations in this form, the exact form what we get through this procedure, these equations are difficult to solve. If we try to solve what we get immediately following this procedure. So some modeling concept also applied there to simplify these two equations. And that is why this model is called two equations model. So we model K equation, we model epsilon equation, we solve for K and epsilon, and then we plug in that K and epsilon value in this relationship. C mu is a model constant. It is usually 0.09 for most of the flows. And then we can find out nu t. Once we find out nu t, we can also find out alpha t. Turbulent Prandtl number is known. And then we can solve these equations to get complete solution of velocity and temperature fields in a given domain. Now, detail of methodology is beyond the scope of this particular course. So, we will go for another approach, which is a very simplified analysis for solving the temperature field and getting the value of Nusselt number at the wall in a pipe flow. So basically what we do, we consider a pipe or circular tube and turbulent fluctuations. If those are averaged out, we get some such profile, and then we say that there is a turbulent core region and very close to the wall sublayer region. This we have already discussed. Now, heat flux due to conductivity of the fluid, that is purely for the thermal conductivity of the fluid, very close to the wall, where effect of turbulence is not felt, we can write QL double prime equal to minus K dt bar dy, del T bar del y. The mean rate of turbulent heat transfer for the turbulent mixing, if we consider the mixing related transport, that is QT double prime equal to rho Cp V prime T prime over bar. And we are assuming that Cp V prime T prime over bar is greater than Cp U prime T prime over bar. So transport in the cross direction, in the normal direction, is more than transport in the streamwise direction, turbulent transport. Also, this is the energy transport due to conductivity of the fluid. And if we add them together, we get total heat flux, which is given by minus K d T bar dy or minus K del T bar del y plus rho Cp V prime T prime over bar. So Q double prime we can rearrange, minus rho Cp we pull outside the bracket. In the bracket then we can write alpha del y of T bar minus V prime T prime over bar. Now turbulent heat exchange is also considered equivalent to an increase in diffusivity of the fluid similar to turbulent momentum exchange. So the way we summarized turbulent momentum exchange, here also V prime T prime over bar can be expressed through gradient transport theory, and it can be written as minus alpha T, that is turbulent diffusivity, into del T bar del Y. So total heat flux we can then summarize at minus rho Cp alpha plus alpha T into del Y of T bar, and alpha T is nothing but turbulent diffusivity or eddy diffusivity. If Q is the total heat transfer, then Q double prime is the heat flux. So Q by A is the heat flux, and we bring rho Cp on the other side. So we can write Q by rho Cp into A equal to minus alpha plus alpha T into del Y of T bar, and we give some identification as A. So we will remember this, and then we will just look at the shear stress in a turbulent flow. That is given by tau by rho. This is again molecular momentum transport, that is basically kinematic viscosity, plus nu T, which is eddy viscosity, into del U bar del Y. We are calling this as B. Now we rely on the Shilton-Colburn analogy at this stage. The analogy says that the heat and momentum are transported as the same rate, that is nu equal to alpha, that is the Prandtl number, which is property of the fluid, which is basically kinematic viscosity by thermal diffusivity, that is equal to 1. That means nu by alpha equal to 1 and nu equal to alpha. Also, this includes turbulent Prandtl number to be 1, which will give us the eddy viscosity equal to eddy diffusivity. So we invoke two assumptions here, nu equal to alpha and nu T equal to alpha T, that is eddy diffusivity alpha T equal to nu T, that is basically the turbulent diffusivity or turbulent viscosity. So turbulent kinematic viscosity equal to the turbulent or eddy diffusivity, nu T equal to alpha T. So if we do invoke these two assumptions and divide equation A by B, we will be able to write Q divided by Cp into A is the area of exchange, into tau du bar equal to minus d T bar, or we can write Q by Cpa into tau du bar equal to minus d T bar. So with this understanding, we go for an additional assumption that the ratio of heat transfer per unit area to shear stress is constant across the flow field. That means from the wall to the center, if we see at any radius, this is basically Q by AT is constant, and this is at the wall is QW divided by AW into tau W. Sorry, Q by A tau. Q, the heat transfer rate divided by A into tau, shear stress. Q heat transfer per unit area to shear stress is constant, and at the wall it is QW divided by wall area into tau W, shear stress at the wall. So now C can be integrated. This equation can be now integrated between y equal to y1 to y equal to y2. So we now go here, rather we integrate this equation, not exactly equation C, this equation, please remember this equation, between y equal to y1 and y2. So we can write QW divided by CP, QW divided by CP, AW into TW, QW divided by CP, AW into TW, and DU bar we integrate between y equal to y1 to y equal to y2. DU bar we are integrating. And on the right hand side minus dt bar. Dt bar also we are integrating between y equal to y1 to y equal to y2. Now this y equal to y1 and y2, these are to be further clarified. One of the limits of integration may be chosen at y equal to 1, conditions prevalent at the wall. The other limit y equal to y2 is chosen in such a way that T bar at y equal to y2 is equal to the bulk mean temperature, and U bar y2 is approximately the same as mean velocity. So see, this mean velocity at y equal to y1 is 0. So 0 to mean velocity we are integrating du bar. Similarly, T bar we are integrating from wall to y equal to y2 in such a way that y equal to y2 give us bulk mean temperature, and y equal to y1 is anyway the wall temperature. So this integration will result in the mean temperature at the wall, and on the other hand mean temperature, bulk mean temperature of the fluid. So QW divided by CP, AW into tau W, integration of du bar, U bar equal to 0 to U bar equal to UM, equal to minus dt bar, T bar equal to TW to T bar equal to TM. Now if we do this, we will get QW into UM divided by AW into tau W into CP equal to TW, the wall temperature minus the bulk mean temperature. On the other hand, we know usually QW, if we express by Newton's law, we can write H AW into TW minus TM, wall temperature minus bulk mean temperature, given by E. Also, if we look at this simple schematic for a turbulent flow, this side pressure is P1, this side pressure is P2 over a length, then we can write this pressure drop delta P into pi d square by 4, total pressure drop, divided by pi dl, that is the area, is equal to delta P by 4 into d by L, and this is basically wall shear stress, because for fully developed flow, wall shear stress is basically the stress component that is developed because of the driven or driving pressure for which fluid is flowing. It just balances the driving pressure force, the shear stress at the wall. So pressure drop in a pipe flow can also be written as del P by rho equal to F L um square by twice T. This is basically Darcy's formula. Del P by rho equal to F, Darcy's friction factor, L into um square by twice T. Now invoking the pressure drop expression in this shear stress expression which we got, if we invoke the pressure drop expression there, we'll get rho F friction factor L um square divided by 4 into twice T d by L, or we can write F by 8 into rho um square. Now this expression for tau W and this expression for heat transfer rate at the wall, if we invoke in this equation, equation D, we will get this relationship 8H AW TW minus TM into UM divided by AW CP rho um square into friction factor equal to TW minus TM. And from here we will get H by rho Cp into Um equal to F by 8. And this is nothing but Stanton number. And Stanton number can also be expressed as Nusselt number divided by Reynolds number and Prandtl number. Nusselt number here has been defined based on the duct diameter or the pipe diameter. Reynolds number has been also defined based on the duct diameter or pipe diameter. So Nusselt number divided by Reynolds number into Prandtl number equal to F by 8. We are identifying this by G. So now we get basically the interrelationship between Nusselt number, Reynolds number and Prandtl number, how they are linked to the friction factor. So also we know from Moody's diagram, if we summarize basically that lookup chart, that what is the friction factor for, if we want to recommend some formula for that, for Reynolds number greater than 2 into 10 to the power 4, it is 0.184 Reynolds number to the power minus 1 by 5. So Nusselt number by Reynolds number into Prandtl number equal to 0.184 Reynolds number to the power minus 1/5, 1 by 5 whole divided by 8. And if we do the algebra, we'll get Nusselt number based on duct diameter is 0.023 Reynolds number to the power 4 by 5. This relationship is good enough but has some limitation because we assume Prandtl number equal to 1. So this doesn't reflect any influence of Prandtl number. So in order to do that, we return to again Chilton-Colburn analogy for energy and momentum transport. The analogy holds good for Prandtl number greater than equal to 0.5. That means for most of the fluids, water Prandtl number is between, depending on temperature of course, between 0.6 and 0.7. Air Prandtl number is 7.2. So we can basically write the Chilton-Colburn analogy as Stanton number into Prandtl number to the power 2/3 equal to CF, skin friction coefficient, by 2. And skin friction, this is the final result of Shilton-Colburn analogy. And this is basically the skin friction factor or Fanning's friction factor. And Fanning's friction factor or skin friction factor is related to Darcy's friction factor this way, CF equal to F by 8. So Stanton number into Prandtl number to the power 2/3 is F by 8. This is the modified relationship to basically include the effect of Prandtl number. Now, this dependence on Prandtl number works well for turbulent pipe flow. According to equation G, that means this equation, then it was earlier Stanton number equal to F by 8. Now it is Stanton number into Prandtl number to the power 2/3 equal to F by 8. So Stanton number into Prandtl number to the power 2/3 equal to F by 8. And friction factor value we can still take 0.184 into Reynolds number to the power minus 1/5. So here we write Stanton number, that is Nusselt number by Reynolds number into Prandtl number. Then Prandtl number to the power 2/3 equal to F by 8. F we substitute by 0.184 into Reynolds number to the power minus 1/5 by 8. And we get the final expression as Nusselt number based on duct diameter equal to 0.023, Reynolds number based on duct diameter or tube diameter to the power 4/5, Prandtl to the power 1/3. Now, this has amazing similarity or match with the experiments, and these experiments were conducted by Dietz and Bolter, and they established experimental correlation which is given by Nusselt number based on duct diameter equal to 0.023, Reynolds number to the power 4/5, and here there is slight modification. Instead of Prandtl number 1/3, it is Prandtl number to the power n, where n equal to 0.4 for the heating case. That means fluid inside the tube is being heated by some high temperature fluid that is flowing or enclosing the tube, so that wall temperature is more, or wall is being heated by electrical heating or any such device where wall temperature is more than the bulkman temperature. Wall temperature is more than the bulkman temperature. That means energy is coming from wall to fluid. It is a case of heating. If it is heating, n equal to 0.4. And if wall temperature is less than the temperature of the flowing fluid inside the tube, then basically it is a case of cooling. So wall temperature is less than the bulkman temperature of the fluid that is flowing inside the tube. It is a case of cooling. And then n is 0.3. So n is 0.4 for heating and 0.3 for cooling. The results have been confirmed experimentally for the range of conditions. We can see the wide range of Prandtl number between 0.7 and 160. So that means oils, etc., all fall in this category. And usual gases, the liquid, water and any other liquid that we come across up to the oils. So over a wide range it is valid. Reynolds number is greater than equal to 10,000. Basically this is for turbulent flow. And L by D greater than 10, that means we allow initial entrance effect. Beyond that, Nusselt number is well predicted by this approximate analysis and by the experimental results, way it was summarized by Ditas and Bolter. All fluid properties are evaluated at the arithmetic mean of bulk temperature. That means bulk mean temperature at the inlet of the fluid, bulk mean temperature at the outlet of the fluid. If we take a mean between these two bulk mean temperatures, whatever is the temperature, fluid properties, like Cp, mu, K, etc., can be chosen according to that temperature, and then Prandtl number, Reynolds number, etc. can be found out, and this correlation can be used, or this relation is also valid. The above mentioned correlations do not apply to heat transfer in liquid metals, because liquid metal, we know Prandtl number is very, very small. So for fully developed turbulent flow in smooth circular tubes with uniform wall heat flux, the recommended correlation for liquid metal, this was determined by this group, Skupinski and the co-researchers, and this has been given as Nusselt number based on duct diameter equal to 4.82 plus 0.0185 into Peclet number based on duct diameter. Peclet number is basically Reynolds number into Prandtl number to the power 0.827. This is for uniform wall heat flux condition. Similarly, for uniform wall temperature, also another correlation determined by Sivan and Simajeki from experimental results, and this is very widely used. It is basically Nusselt number based on duct diameter equal to 5.0 or 5 plus 0.025 into Peclet number, that means Reynolds number into Prandtl number, and Reynolds number is determined based on the diameter of the tube. So Peclet number based on duct diameter or tube diameter to the power 0.8. So here Peclet number to the power 0.827, and here it is Peclet number to the power 0.8. And this is for uniform wall temperature condition, and this is for uniform wall heat flux condition. So for liquid metal, we use these two correlations. One is for uniform wall heat flux, another is for uniform wall temperature. Otherwise, for turbulent ducted flow, we can use this correlation for fully developed turbulent ducted flow very comfortably. It has been determined for tube, can be extended to other ducted flows. Only thing, Reynolds number has to be determined based on hydraulic diameter, and the same hydraulic diameter will be used for determining Nusselt number. So we come to an end of this lecture. Thank you very much for your interest.